In chapter 2, we saw reflex agents that map states directly to actions. This work only in simple environments. Goal-based agents, however, consider future actions and the desirability of outcomes. One type of goal-based agent is the problem-solving agent. Problem-solving agents treat states as atomic. They see the world as a set of discrete states without internal structure. Their task is to find a sequence of actions that achieves a goal. And for that, they search the state space. So these slides are available online and was created by some person named here. And we are using this slide to guide our discussion of the chapter 3 of the Russell Norvich's textbook. So these are the outlines, and we talk about an example. Let's say the example is a little bit down below. Let's say, imagine an agent touring Romania. Its goal is to reach Bucharest, which is here. And by adopting this goal, it can ignore irrelevant actions like sightseeing detours, simplifying decision making. Let's say the agent is currently in Arad, which is here on the left side of the map, and Bucharest is more on the right side with 4 or 5 nodes in between them. And this is a graph. So the agent formulates the problem by deciding which states and actions to consider. Using a map, it can simulate future steps from its current city to Bucharest, choosing the path that reaches the goal. If the environment is observable, discrete, known, and deterministic, the agent can plan a fixed action sequence. Please understand, observable, discrete, known, and deterministic. Then only the agent can plan a fixed action sequence for coming from Arad to Bucharest, or from one node in a graph to another node where this is a connected graph. The agent can plan the fixed action sequence through 3 processes that it needs to follow. The first one is formulate a goal and problem. The second one is search for a sequence of actions that achieves the goal. And the third one is execute the solution step by step. Now, why we say observable, discrete, known, and deterministic? Let's see with respect to this Romania map or graph. The environment properties directly affects how predictable and reliable the agent's actions are. Let me break it down. Observable because the agent can fully perceive the current state. It knows exactly where it is and what's happening. If it could not observe everything, it might have to guess or update its plan dynamically. So it knows where it is. Discrete because the environment has a finite number of distinct states and actions. At every point, it can only go to a fixed number of next states through the connecting edges. This makes it possible to enumerate all possible paths and plan a specific sequence. In continuous environment like steering angles, how the steering angles move in driving, there are infinitely many possibilities, so a fixed sequence isn't practical. Now, why the environment needs to be known? The agent knows exactly how its actions change the state of the environment. Without this knowledge, the agent could not predict the outcome of each step. So a fixed sequence might fail. It's something like, okay, if I'm in Arad, I go 140 miles, which is the age weight between Arad and Sibiu, I'll reach to Sibiu. So it knows exactly how its actions change the state of the environment. The agent will come to Sibiu. The fourth point is deterministic. Each action has a predictable outcome. If actions were stochastic or uncertain, like even if I travel this 140 miles, I will not reach Sibiu, so it's like throwing a dice and it's a chance factor, then it's not deterministic. So we don't want any actions which are stochastic or uncertain. The agent could not guarantee in that case that following a fixed sequence would achieve the goal. That means through that path it will be able to reach Bucharest. So that's why we said we need the environment to be observable, discrete, known, and deterministic. In that case only the agent can plan a fixed action sequence. Now, to solve a problem, we need a few things. The first one is initial state. Okay, like here it's at Arad. So initial state is basically where the agent starts. Okay, now there can be many actions, okay, or successor functions. So the set of actions available in each state, like from Arad, it can say that go to Sibiu, or go to Timisoara, or go to Zerind. Next is a transition model we need, which is the successor function is basically the actions and the transition model together. So the transition model defines the result of each action. Basically what it means, like if it's the result of in Arad and then go to Zerind, you reach in Zerind. From Arad, if you take the action go to Zerind, you reach to Zerind. So that means these are also called like successor states, so successor functions. And together with the initial state, they define the entire state space. Like you are in a particular position, you take an action, and then you reach to a next state. So that state is also now included in the successor function, and together all those states create the state space, which is nothing but a network of all reachable states. Now the next thing is the goal test. It determines if a state satisfies the goal. Okay, in our example, the goal is in Bucharest. That means I want to reach Bucharest. In other cases like chess, the goal might be conditions such as checkmate. And the next or the last thing is the path cost, which assigns a numeric cost to path. Like here we said age weights. Okay, so the path cost is sum of distances or number of actions executed. So here for Romania, this could be the total distance traveled, okay, to reach Romania from a particular start state. So the step costs are denoted by C, X, A, Y, which means that for taking an action A in state X, we reach Y. So the solution is a sequence of actions that takes the agent from the initial state to a goal state. And the optimal solution is the one with the lowest path cost. Now, formulating problems, selecting state space is not easy, okay? We need to abstract some details. Abstraction is an important thing, okay? Abstracting the unnecessary details. So that's what we will look at it. So what we are saying when we define a problem like driving to Bucharest in this map again, we create a model, an abstract description of the real world. The real journey includes countless details like companions who are traveling with you, radio programs, what you are listening to, road conditions, snowy, rainy, sunny, broken roads, or many different other conditions. Most of these are irrelevant to the goal. The process of removing unnecessary details is called abstraction. We simplify both states and actions, okay? States in Arad instead of every detail of the world. I don't need to know where is Arad and what it's doing. When we are abstracting it out, Arad is the starting state, that's all. And action is very simple, go Sibiu, instead of turning the steering wheel 1 degree at a time. We don't need that much detail. A good abstraction captures the essential elements while leaving out irrelevant complexity. For example, an abstract path like Arad, Sibiu, Râmnicu Vâlcea, and Bucharest represents many possible detailed routes. As long as each abstract step can be executed in the real world, the abstraction is valid and useful. Without effective abstraction, intelligent agents would be overwhelmed by the complexity of the real world.